The topic of this video will be reactions of ketones and aldehydes. We will discuss many reactions of ketones and aldehydes, but the majority of these will all be nucleophilic additions to the carbonyl. All of these reactions take a similar form, as do their mechanisms. In all of these reactions, we will add a proton to the oxygen of the carbonyl and a nucleophile to the carbon of the carbonyl. This will produce a tetrahedral product. All of these mechanisms will have in common the tetrahedral intermediate. The difference comes from the order of addition of the proton and the nucleophile. The mechanism that a particular nucleophilic addition reaction takes will depend on the structure of the nucleophile. However, all of these mechanisms go by one of two pathways. A nucleophilic addition can be acid catalyzed, where the proton adds to the carbonyl first, or a nucleophilic addition reaction can undergo a base catalyzed mechanism, in which the nucleophile adds to the carbonyl first. Now let's look at these two mechanisms in more detail. Nucleophiles that undergo an acid catalyzed mechanism tend to be weaker. Therefore, we typically need to strengthen the electrophile, which is the carbonyl, through protonation. This is why this mechanism requires an acid catalyst. In these reactions, the nucleophile and the acid catalyst are typically added in the same step. Remember that in the acid catalyzed mechanism, the nucleophiles are typically weaker. The reason that they're weaker is they're typically a protonated nucleophile. For example, an alcohol rather than an alkoxide ion. This is why these weaker nucleophiles require the acid catalyst. The electrophile needs to be protonated prior to attack of the nucleophile. Protonation of the ketone or aldehyde makes it a better electrophile. This protonated carbonyl has a resonance structure. The protonated carbonyl is now a much better electrophile that can react with our weaker nucleophile. This produces the tetrahedral intermediate. The final step of the acid catalyzed mechanism is deprotonation to form the neutral product. Some base, typically the nucleophile itself, will deprotonate forming the alcohol product. The product of this reaction is the result of the addition of a proton and the nucleophile across the double bond of the carbonyl. When we look at the base catalyzed mechanism, the product will be the same, but the order of addition of the nucleophile and the proton will be different. Nucleophiles that tend to undergo a base catalyzed mechanism tend to be stronger. Because the nucleophile is stronger, we don't need to strengthen our electrophile prior to nucleophilic attack. Therefore, the order of addition of the nucleophile and the proton occur differently than they do in the acid catalyzed mechanism. In the base catalyzed mechanism, the nucleophile is added first, and this is typically followed up by an acid workup step. The first step of the mechanism is attack of the nucleophile on the carbonyl. This forms the tetrahedral intermediate. It is during the acid workup step that the alkoxide ion is protonated. This produces the final product. Notice that the final product is the same as the one that we saw for the acid catalyzed mechanism. Both of these mechanisms result in a product that involves addition of a proton and a nucleophile across the pi bond of the carbonyl. It's just the order of addition of the nucleophile and the proton that differs. Most of the reactions of ketones and aldehydes that we will look at follow one of these two mechanisms because they are a nucleophilic addition to a carbonyl. Remember that when trying to determine the mechanism of a new nucleophilic addition to a carbonyl, you want to consider the strength of the nucleophile. Strong nucleophiles will follow the base catalyzed mechanism. Weaker nucleophiles will follow the acid catalyzed mechanism because they require protonation of the carbonyl prior to being able to attack the electrophile.